Okay, this is a digital image processing lecture number 5. Today, I'd like to talk about image compression, discretization, digitization, and there are two effects here. Previously, I show you a little bit. For instance, you have some sample and quantization. We have n by m point array of the sample from this matrix F00 to Fnm, and F is the uh, value of the uh, brightness, I mean the illumination at each pixel, a picture element in this matrix, because each the appearance of the picture concentrate. It involve illumination and reflection. So and then that is fx is rxy by Rxy. I is the intensity foot candle, and R is the reflection 0. It depends on the material, and this depends on the brightness of the picture. So, okay, but anyway, this you have the picture which is discretized, sampled, and then digitized. Okay. I wanted to show you here. I previously yellow it. For instance, you have a n by m sample here. This is the process n by m, and the number of discretization and the number of bit is like this. If n and m is same, so number of bit is n squared multiplied by m. For instance, 128, and multiplied by 8, or so on. And also here in this table, you see the m from 1 to 8 bits per pixel, and this is from the image size from the 32 to 1024, for instance, in vertical and horizontal. It can be same or different. But for instance, if you increase m and 32n is decreased, you have 4096 bit. Also, if you decrease m1 and increase n is also 4096. So which is better? The number of the quantization is same, but the preference on what your subjective quality is different. Which is better, to increase m or increase n? That is the question of this section. Also, you can use it in bit number, also in byte, which is 8 bit is 1 byte. So divide this number by 8. So 8 bit is 1 byte for various storage. And then is, for instance, the previous 512, 4 bytes. Okay, we have two effects. One effect is the effect of the discretization, where if you, for instance, figure 9 show you the 512 to up down to 32 by 32. So if you decrease the number of discrete or sampling point, you will see the mosaic effect from here to here. Gradually here you see, and here is 32 by 32 sample is decreased. On the other hand, if you decrease m, number of the quantization, m, for instance, here figure 10 is here in this figure, from 1024 to up to 2 level. This is 1024 up to 2 level of the quantization. Here, figure 10 illustrates the from this 8 bit to 1 level, 7 to 1, m is 1. This effect caused this is a different effect. This is false contouring. This effect, the effect of the reducing the number of the quantization, is the caused by insufficient number of the gray level in a smooth area. So you will see the false contouring here. False contouring, because, for instance, if you have the place you have um, less activity, but you should assign more uh, discretization and less, but quantization should be more bit, because otherwise you will see the false contouring like this. I'll show in detail later. So we have two varying n and m, and then we'll see the isopreference curve. I will show curve with respect to the n and m plane. So what is isopreference curve? Here is showing the isopreference curve for A and B and C. What's the A is the picture of low activity. B is picture of cameraman less activity, and C is the picture of the crowd of for more activity. So the places you have less activity like this one, so you need less sample here. But a little, if you have different of the gray level here, you need more sample here. So it's a variable sampling here. You need also for crowd, you don't need the you need more sampling, of course, but you don't need more quantization. Here you need quantization. Here you don't need quantization. So later I will tell you about non-uniform sampling and quantization. First of all, let me talk about the isopreference curve. Isopreference curve, as shown in figure 2.12 for ABC, ABC. There are three effects here, from right to left. This result suggests that one, as expected, the quality of the image tends to increase with increasing M and N. This is of course. But in some cases, the quality improved by the decreasing N. In fixed N, for even fixed N, quality improved by decreasing N. Even M, number of the bits, from 5 to 4. If you decrease even the quality, doesn't matter. The most likely reason for this result is that the decreasing M results increasing the appearance and contrast of the image. So this is result number one. The result number two, the curve tend to become more vertical as the detail of image increase. So in this one, the isopreference become more vertical. Rather, in low activity is more curvy. The result showed that they become more vertical. The curve tend to become more vertical. This result suggests that the image with a large amount of the detail, only a few gray level is enough. Needed, for example, for C is 64 for 128, only few bits. I mean, improve, M doesn't matter. Quality is improved by increase M. For E, this quality is not improved. The quality is not improved if you increase the M. This is because as I said, the M doesn't matter for high uh, activity. The same is not true for the figure number 3, this one. So, okay. So the number 2 is they tend to become more vertical in high activity. So even less, with high activity, even you can decrease the number of the bit quantization. Number 3 is the isopreference curve depart markedly from the curve of the constant beam. Constant beam line are this dash line, just multiplication of n square by m. So it's just constant bit rates, okay? And but in low activity, this depart from this because it's isopreference. They ask the people which is better for you, and for low activity they say. That's why here it's important for non-uniform sampling. For fixed value of the spatial resolution, the appearance of the can be improved in many cases by using the adaptive scheme where the sampling process depends on the characteristic image. In general, the sampling is required in the neighborhood of the sharp gray level transition in sharp level, whereas a coarse sampling may be utilized in the relatively smooth region. This is a smooth region. This is more high activity. Consider, for example, a simple image consists of the face superimposed on the uniform of the background. Clearly, the background carries the detailed information can be quite adequate representation of the core sampling. The face, however, contains less content, more detail. The face, however, contains more conserved detail if the additional sample not used in the background or used in the region of the image. So if you assign more sample, not here, but here. So number of samples same, but the representation of the image is better. Is non-uniform sampling. Also, non-quantization is like this, that the place you need more quantization, here you don't need more quantization. And uh, they play in high activity, you need become vertical, so you need less quantization, so you need less quantization here. When you have high activity, you decrease the number of the increase the sampling, but decrease the number of quantization. These two effect is very important for compression of the digital image, or for digital image, or this digital movie in digital camera or digital cinema, or whatever, that there are now standardization in JPEG and MPEG group, that it is quite standardized for compression, very low bit rate with high quality of image. Because of this, if you consider, of course, there are many complicated algorithms in this case. And also, I wanted just to here just to emphasize about musaic effect for sampling, also false contouring for less digitization, also isopreference. This in this lecture, isopreference curve are trying to become more apart from the actual bit rate, but more vertical in high activity. So for low activity, you have less sample. High activity, you have more. You need more sample. So the number of the sample is same, but you can what is look is better, looking better. Also in in high activity, like this crowd, you need you need more sample, but less bits. Only one bit is maybe enough. That's why you can represent the image in better. That's I mean, what I wanted to tell you. This image, I cannot switch to the other here in other PowerPoint. You can use the PowerPoint in the lecture number 4 to see what I mean here in more detail there, but here is also enough to see. And here I stop this lecture and stop sharing, recording here, and thank you very much.